Hello and welcome back. In this video, I want to talk about something called relative velocity. And relative velocity is the velocity of an object as seen by a moving observer. Okay? And many of the equations that we're going to see in this lecture, they're things that you already know. They're really obvious equations. But what I'd like to do is I'd like to formalize these equations and actually write them down so that we can expand upon them and solve problems that are maybe not so obvious. So in order to do this, in order to formalize these equations and actually write them down, I need to introduce some notation. So the way we describe the velocity of them with respect to you is like this. It's the velocity of them with respect to you. So it's always the velocity of the object with respect to the observer. Okay, so the first index is the object, the second index is the observer. And like I said, many of these equations that we're going to see, they're really obvious equations. And so I just want to introduce this by looking at a couple of simple examples. So the first example says, a train is moving 10 meters per second as seen by an observer on the ground. A man in the train is walking down the train with a speed of 2 meters per second as seen by the passengers on the train. How fast is the man walking down the train appear to be moving as seen by the observer on the ground? So let me go ahead and draw a picture of this. So what we have here is we have a train. And the train is moving at 10 meters per second. And if I wanted to write this in our notation, we would say that this is the velocity of the train with respect to the ground is 10 meters per second. And inside the train is a man who's walking down the train. And his velocity, this is the velocity of the passenger as seen by the people on the train. So this is the velocity of the passenger with respect to the train is 2 meters per second. And here's my observer on the ground. And I want to know what the velocity of the passenger on the train is as seen by the observer on the ground. So what I'm looking for is I'm looking for the velocity of the passenger with respect to the ground. And the thing is that we already know what this is going to be, right? We don't have to do any calculation. We know, okay, well, the train's moving to the right at 10 meters per second. There's a man inside the train. He's moving in the same direction at 2 meters per second. So the person here on the ground, he's going to see this person on the train moving to the right at 12 meters per second, right? So the person on the ground sees the man in the train moving to the right with a speed that's equal to the speed of the train plus the speed that the man moves down the train. So the way we would write this in our notation is this is the velocity of the passenger with respect to the train plus the velocity of the train with respect to the ground. And one thing I want to point out about this, firstly, this equation is really obvious, right? You knew that what the answer was going to be before I even wrote down this equation. So this is an equation that anytime you forget it, it's really, really easy to just re-derive it again, right? You just think through the simple scenario again, and you'll immediately arrive at this equation. The other thing that I want to point out, just like a little bit of a thing you can use to help remember this formula, is that notice that the first index here is the first index that appears in the equation. And the last index here is the last index that appears in the equation. And these equations in between, these indices in between, are always the same. So that's a very easy way to remember this. So if I wanted to just write this equation down, right? The velocity of A with respect to B is equal to the velocity of A with respect to C plus the velocity of C with respect to B. Okay? And this equation, it's always going to be true. Okay? It doesn't matter what A, B, and C are. And one thing I should point out about this is that this equation works in the x direction and it works in the y direction. So I can combine these two, the x direction and the y direction, and I can write this as a vector equation. And this is where writing this down as an equation becomes a really useful thing, right? Because it may not be so obvious if these things are moving off at different angles what the equation is for finding the velocity of an object with respect to a moving observer. Now, let's just go ahead real quick and just plug these numbers in. We should see that this is going to make sense. So the velocity of the passenger with respect to the train, that's 2 meters per second. The velocity of the train with respect to the ground, that's 10 meters per second. And we see that we do in fact get 12 meters per second, as the equation was designed. So this is a very simple equation, very easy to derive. There's one other equation. So I want to look at this second example. The question says, what is the velocity of the man on the ground as seen by the man walking in the train? Right, so we've got a train, and inside the train is a man who's walking down the train at 2 meters per second. And the question is, if he looks out the window, he's going to see this person on the ground. And this person on the ground is going to appear to be moving. And the question is how fast does the person on the ground appear to be moving with respect to the person on the train? And again, like I said, these equations, they're equations that you already know, right? So if you think about a simple example, you're driving down the road going 20 miles per hour, you look at a mailbox on the side of the road, well, the mailbox looks like it's coming at you, right? It looks like it's traveling in the opposite direction that you're moving with the same speed. So, right, if this person here is moving to the right at 12 meters per second, he looks out the window, he sees a person on the ground, it looks like that person's traveling in the opposite direction at 12 meters per second. So the way we would write this is we'd say the velocity of the person on the ground as seen by an observer on the train, the passenger on the train, is equal to minus the velocity of the passenger on the train as seen by the observer on the ground, right? So they're the same, but in opposite directions. So let's go ahead and look at a couple simple examples. So this first example, it says a boat is moving across a river, and the boat has a velocity with respect to the water that's equal to 3 meters per second in the x direction and 0 meters per second in the y direction. So this is the velocity of the boat with respect to the water, okay? Now, the water is flowing down the stream, and it has a velocity as seen by somebody who's standing on the shore, or the ground, or whatever it is. It's equal to this. So this is the velocity of the water with respect to the ground, and it's 0 meters per second in the x direction, and 1 meter per second in the y direction. So let me go ahead and open up a blank sheet, try to remember what these numbers were. So we found the velocity, or we were given the velocity of the boat with respect to the water was plus 3 meters per second in the x direction, 0 meters per second in the y direction, and the velocity of the water with respect to the ground was 0 meters per second in the x direction and 1 meter per second in the y direction. So if I just go ahead and draw a picture of this, right? So what we have is we have the water is moving in the y direction, right? So there's this water, it's moving in this direction up at 1 meter per second. And in the river, there's a boat. And this boat is moving to the right, as seen with respect to the water, at plus 3 meters per second. So what this means is that if I were on this river, if I were just lazily floating like on a tube down this river, then I would see this boat moving to the right at 3 meters per second. But of course I would be moving down the river at 1 meter per second. That means that this boat is also moving down the river at 1 meter per second. Right? So we can already we already know what the answer is going to be. And these equations, they're really easy, right? So this boat, as seen by the observer on the ground, it's moving 1 meter per second in this direction and 3 meters per second in this direction, right? So it's moving something like this. But let's go ahead and just write this down. So what we're looking at is the velocity of the boat with respect to the observer on the ground is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the observer on the ground. And that's plus 3 meters per second, comma 0 meters per second. That's the velocity of the boat with respect to the water. The velocity of the water with respect to the ground, that was 0 meters per second in the x direction, 1 meter per second in the y direction. So, in fact, we do see that the boat is moving 3 meters per second in the x direction and 1 meter per second in the y direction, right? So it's moving 1 meter per second downstream, 3 meters per second across the stream. So let's go ahead and look at one more example. This is a little bit more challenging. So the example says, an airplane measures the wind around the plane as having a velocity of 100 meters per second north of east. Okay, so this is the wind moving around the plane. And the velocity of the wind measured on the ground is 5 meters per second, 60 degrees south of east. So the question is, what is the speed and the direction of the plane with respect to the ground? Okay, so the airplane, it's measuring this wind around it, but it's this artificial wind because the plane is moving very, very quickly through the air. Okay, and that's this 100 meters per second, 30 degrees north of east. And if the air were perfectly still, this would tell the plane how fast it's moving and in what direction, but the air is moving with respect to the ground, and so now we have to do a calculation to find how fast this plane is moving with respect to the ground, and in what direction it's moving with respect to the ground. So, the equations that we have, right, they all involve adding or subtracting vectors, right, these velocities. So remember that anytime you have to add or subtract a vector, the first thing we have to do is we have to write the vector in component form. That way we can actually perform the addition or subtraction. So let me go ahead and actually just write these in component form. So this is the velocity of the wind with respect to the plane. It points 30 degrees north of east. So if this is north and this is east, then the wind looks something like this, right? It's pointing 30 degrees north of east. This angle here is 30 degrees, right? That's what we mean, 30 degrees north of east. That means this angle here. So again, using my normal vector notation, where I take the first component as being the east-west component, then we can see here this east-west component is adjacent to the angle 30 degrees. So we would say that the first component of the velocity of the wind with respect to the plane is 100 meters per second. And because it's adjacent to the angle 30 degrees, we have cosine of 30 degrees. The y component is in the north, so that's the positive direction. It's opposite the angle 30 degrees, so we use 100 meters per second times sine of 30 degrees. So if I plug these numbers into a calculator, I see that this is equal to 86.60 meters per second in the east direction and 50.00 meters per second in the north direction. And I'm keeping all of these digits because the effect that this wind is going to have is going to be very, very small, right? This is a very, very small velocity for the wind and a very large velocity for the plane. So this is only going to have a very small effect. Now, we'll have to decompose this vector as well, so the velocity of the wind with respect to the ground. So let me go ahead and draw a picture of this. This is 60 degrees south of east. So here's east, here is south. All right, so 60 degrees south of east. That means looking at something like this. This is 5 meters per second, and it's this angle here that's 60 degrees, right? If we're 60 degrees south of east, then it's this angle. So again, the east-west component is the first one. We can see it's in the east direction. That's the positive direction. This side here is adjacent to the angle 60 degrees, so we have 5 meters per second times cosine of 60 degrees. The north-south component is in the south direction. That's the negative direction. So we have a minus. And this is opposite the angle 60 degrees, so we get sine of 60 degrees. And again, if we plug this into a calculator, this time we're going to get 2.500 meters per second in the east direction and 4.330 meters per second in the south direction. So these are our two velocities. Okay? So the question is, how do I find the velocity of the plane with respect to the ground, right? So I've been given, let me write this down. So we found the velocity of the wind with respect to the plane. This was 86.6 meters per second and 50 meters per second. And the velocity of the wind with respect to the ground, this was 2.5 meters per second and minus 4.33 meters per second. So I'm looking for the velocity of the plane with respect to the ground. So we know from our equations, this is the velocity of the plane with respect to the air, or the wind, I should say, the wind, plus the velocity of the wind with respect to the ground. Now I know the velocity of the wind with respect to the ground, so I could plug this number into here, but I don't know the velocity of the plane with respect to the wind. What I was given was the velocity of the wind with respect to the plane, not the velocity of the plane with respect to the wind. But we know how these two things are related, right? The velocity of the plane with respect to the wind is minus the velocity of the wind with respect to the plane. So this is minus the velocity of the wind with respect to the plane plus the velocity of the wind with respect to the ground. So now all I have to do is plug these two things into this equation, and what I'm going to get is I'm going to see that this is minus 84.10 meters per second in the west direction, and we have minus 54.330 meters per second south, right? And of course this makes sense, right? If the wind around the plane is moving east and north, then that means the plane is actually moving south and west. And this air around it really doesn't have a whole lot of effect. We can see that these numbers are pretty similar to just minus these numbers. So the very last thing, I asked for the speed that the plane was traveling at and the direction it was traveling at. So we need to actually find the magnitude and direction of this vector. So we found the velocity of the plane with respect to the ground was minus 84.1 meters per second in the x direction, or the east direction, and minus 54.33 meters per second in the north direction, or 84.1 meters per second west, and 54.33 meters per second south. So the magnitude of this, so the vector, the magnitude is the x component squared. So we have minus 84.1 meters per second squared, and then the y component squared, so 54.33 meters per second squared, and then you square root the whole thing. So plugging this into a calculator, we see that this is 100.1 meters per second. So not a whole lot different than the speed of the wind around the plane. If you remember, that was 100 meters per second. So it's not a big surprise. The air wasn't moving very quickly. So what about the direction of the plane? So this will actually change quite a bit more than the speed. So let's see. Let me go ahead and draw a little picture of this. So the vector that we're looking at, okay, this vector has a component that's in the west direction and a component that's in the south direction. So it looks something like this. Okay, this is the velocity of the plane with respect to the ground. Okay. And I know this, right? This is 84.1 meters per second. I know that this is 54.33 meters per second. So if I want to describe it in terms of this angle right here, I know the opposite and I know the adjacent, right? So I would say theta is equal to arc tangent of 54.33 meters per second divided by 84.1 meters per second. So if I plug these numbers into a calculator, I think what you get is 32.86 degrees. And then again, remember, anytime you have to describe the direction of a vector as an angle, you always have to say how the angle's measured. So this angle was measured south of west. And again, if we think back, the air around the plane was traveling 30 degrees north of east. So if we just reversed that, we'd say the plane was traveling 30 degrees south of west, But we can see now that's actually not the case. The plane's traveling 32.86 degrees south of west. So I think that'll be the last example on relative velocity. And in the next set of lectures, I'm going to begin talking about Newton's laws.